All attendees are in listen-only mode.
Hello everybody, welcome to part 3 of our webinar series on soil liquefaction. This is actually webinar number 9 out of all of our webinars, but it's part 3 on the soil liquefaction segment, and today's webinar is going to focus on worked examples. So we will have a number of slides at the beginning, and then we're going to move over to the software program CLiq, and Dr. Robertson is going to work through some examples for you. And then at the end, we will be sort of raffling off a number of licenses for the software. So stay tuned, and we'll have a question for you to email your answer in, and good luck on that one. So I will pass the mic over to Dr. Robertson now and start the webinar.
Thank you, Kelly. Well, welcome everybody to this 9th in our series of webinars. And as Kelly said, this is the 3rd one in the series of evaluating soil liquefaction using the CPT. So it's building upon the first 2. So hopefully those that attended the first 2, it'll feed directly into that. And those that didn't, hopefully you'll be able to follow along reasonably well. And so just a reminder of what the definitions of liquefaction are. You know, in part 1 we talked about cyclic or seismic liquefaction. And this is when, typically in an earthquake, when you get cyclic loading, and that can result in a buildup in pore pressure in loose sands, and then a decrease in effective stress, and eventually reaching the condition of essentially zero effective stress, where you get essentially a complete loss of stiffness in the ground, and that results in large deformations during the earthquake. But once the earthquake finishes, those deformations tend to stop, other than the post-earthquake vertical consolidations that result in settlement. And then in part 2 we covered flow or static liquefaction, and this is where you have a strain softening response that can be triggered either static or cyclically. So earthquakes can trigger flow liquefaction, but also the case histories have shown that they can be triggered statically as well. But the term liquefaction has been used to describe these, and it's a completely different mechanism, although the two often look somewhat similar in terms of the large deformations. And so in our worked examples, we're going to try and show both examples. Initially, I'll start off with seismic liquefaction and then show some examples of static liquefaction. So for seismic liquefaction, you know, it's usually linked to level ground conditions or gently sloping, or level ground conditions near a free face, some slope where there are some static shear stresses that can drive some lateral spreads. And we discussed that the sequence would normally be evaluate whether or not the materials are susceptible to cyclic liquefaction, and then if they are, evaluate whether or not the earthquake would trigger liquefaction, and then if it does, then estimate post-earthquake deformations. And that would be either vertical reconsolidation settlements, where, you know, these materials have essentially reached zero effective stress, so they reconsolidate, and that results in volumetric strains that accumulate to reconsolidation settlement. And then also, if you do have some driving shear stresses, such as a nearby free face or a slope, then those shear stresses can induce lateral spreading during the earthquake. So that was the sequence. And so what I'm going to do is illustrate some examples through this software. And those of you that have followed these webinars, you know that previously I showed the basic CPT interpretation program, which is called CPT. And after we developed CPT, we then worked on this sort of companion program that's structured the same way, but it's focused on liquefaction analysis. And it's called CLiq, so some people say CLiq, but we prefer the term CLiq. It's a nice, slick little program. And it was developed in partnership with John Ioannidis of Geologismiki in Greece. And so you download it from the same website as CPT. And John actually bundles the two together, so if you want both, there's a slightly reduced price when you get the both. But essentially, they each sell for, I think, 199 euros, which is a little over $230, a little less than $250 US. So excellent price for such a powerful little program. So that's what I'm going to use. But before I go over to the program, I want to sort of set the stage for maybe some of the worked examples. And in part one, I did show some cyclic liquefaction examples, and one of the best ones is some sites from Moss Landing. Now, Moss Landing is located in Monterey Bay in California, just south of San Francisco, and it suffered fairly extensive liquefaction during the Loma Prieta earthquake. And the Loma Prieta earthquake occurred in 1989. It was roughly a magnitude 7 earthquake that occurred actually quite close to Monterey Bay, quite close to Moss Landing, only about 21 kilometers away from Moss Landing, so quite close. It was a pretty big earthquake. I mean, 62 people were killed in total, 12,000 people were made homeless, and the damages, I think, were in excess of $10 billion, and that was back in 1989. And as I said, there was a fairly extensive liquefaction occurred, and so there was a very nice report written by Professor Bollinger and Idris from UC Davis, and it was published in 1995, that does a very nice job summarizing all of the case histories at Moss Landing and presents the CPT and SPT data, and that was where, for example, this cross-section at State Beach. So State Beach is actually on the north side of Moss Landing, and there was fairly extensive liquefaction of the road in towards the harbor at Moss Landing. And UC 14 and 15, 2 CPTs, were very close to the entrance kiosks on the road. And then a little bit further back was UC 16 and 17, and then further back up on the sand dunes was UC 18. And it's quite nice because liquefaction occurred and there was a lateral spread towards the harbor side. And most of the movement occurred close to the harbor side near UC 14. And then further back at UC 16, the sand's a little denser and the movements were less. And then by the time you got back to UC 18, the sand is even denser up in the dune area, and there were no lateral displacements. So we'll just look at UC 14 and 16 as an example. And we start off with this one because it is a relatively clean sand in the upper 6 or 7 meters, so it's quite a nice example of a clean sand liquefaction. And during part one presentation, I did show where the data fit on the normalized soil behavior type. And here's the various case histories, the solid dots being the ones that liquefied, the open ones being the ones that didn't liquefy. And UC 14 is plotting up in the sand region, friction ratio of about 0.5%, and the data point plots up in that clean sand region. We're also going to look at UC 8, which was the marine lab site, and it is a silty sand, so it has a lower cone resistance but a higher friction ratio. And as we discussed, they have similar clean sand equivalents, which is quite nice as an example. So they both have the same clean sand equivalent, even though they had different fines content and cone values and different soil behavior type indices. So that's what we're going to look at, and this was the profile I showed. So what I'm going to try and do now is sort of get out of the slides and switch over to the software. And so here's the software, and I've already opened it up, and I've loaded in these example profiles. I'm going to work my way through a number of these to try and hit some main points. So the software is structured in a similar manner to the way CPT was. And those of you that have watched the previous webinars notice that one of the challenges we have with my computer is that when I'm doing the webinar and I switch between PowerPoint and the software, my computer freezes for a little while. And that's exactly, of course, what it's done again here. So I'm going to sort of talk my way through, hoping that my computer is going to wake up a little bit when it gets, and it's a feature of I have a Mac, and so the webinar is coming through on the Mac side of my computer, and the PowerPoint and the software is running on the Windows side of my computer, and it's when I switch between the two that gives me the this problem of freezing. So hopefully, okay, I think it's trying to wake up. So please bear with me. I'm going to close it so I can open it again. So you're actually going to see me open the program. So I'll minimize that. So by reopening. So you see the little logo pops up when you open the program, and then because it's already a project file, I just open a project file where I'd already loaded these, see the liquefaction examples. So here they are now. We're back again. So we're going to look at UC14 first. So here's the basic cone data, the interpreted plots, so cone resistance, friction ratio, pore pressure, and soil behavior type, and then there's a set of normalized plots. So if I look at the basic plot, you can see that you've got sand down to about 8.5 meters. There's a little clay layer from 8.5 to 9 meters, then a sort of a silty sand region, then it drops down into a softer clay from 12 meters on down. This sounding went to 22 meters. So you see this little clay layer from 8.5 to 9 meters and mostly sand above. And if you look at the pore pressure profile, you can see that it's essentially hydrostatic in the upper sand. So the water table is at about 1.8 meters below ground surface. It's hydrostatic, and then you get this excess pore pressure in the soft clay layer. And then in the siltier sand below, it's sort of it's a little denser, so you get slightly negative pore pressure, and then those pore pressures come positive as you come into the softer clay. And so you've got the normalized plots, and they confirm you've got a fairly large normalized cone resistance friction ratios, just under 0.5%, and the BQ value is essentially 0, of course, because there's no excess pore pressure. And there are a number of tabs, so there's a bunch of liquefaction tabs, and under the liquefaction tabs, the first one is, again, the cone resistance, IC, the normalized cone resistance, and then that correction KC, which is essentially that fines content correction. And you can see in the upper clean sand there is no correction, so KC varies in this case from 1 to 20, and in the clean sand it's 1, there is no correction. It's a multiple correction, so you're multiplying by 1. And then when you get into the silty sand and the clay below, the correction picks up, and then the calculated clean sand equivalent. And then you get to the actual cyclic liquefaction plots, and you get a plot of cyclic stress ratio, cyclic resistance ratio. So for a given earthquake, and I'll go to that tab in a minute, the red line shows the cyclic stress ratio from the earthquake, and the purple line is the cyclic resistance ratio. So where the cyclic resistance ratio drops below the cyclic stress ratio, then it's predicting liquefaction. And then there's a plot of factor of safety, and then the next plot is Iwasaki's liquefaction potential index. And I don't think I actually talked about this in part 1, but Iwasaki's liquefaction potential index was a clever idea where he observed that it's not just the factor of safety, it's how much soil liquefies and how close it is to the surface. And so he came up with a system of weighting the factor of safety as a function of depth. And so he weighted it linearly from a factor of 1 at the ground surface down to 0 at 15 meters. So he said if you had liquefaction closer to the ground surface, that would create more damage than if you had liquefaction deeper. And if you had liquefaction greater than 15 meters, then essentially it resulted in almost no damage. So we have this weighting factor, and it was multiplied by 1 minus the factor of safety. So every time the factor of safety got less than 1, then you would calculate this weighted number, and then you would sum that up over depth. And you see that's what this line shows as it's summing up. And you see that in this case, most of the liquefaction occurs from the water table at 1.8 meters down to about 5.5 meters. And there may be little bits of liquefaction below, but most of it occurring in that upper portion. And so you can see the liquefaction potential index builds up in that upper portion, and then not very much happens, maybe a little bit down at 10 meters, but then essentially nothing. And Iwasaki defined some ranges and said if the liquefaction potential index was less than 5, so when you summed this up, if it was less than 5, then essentially you would have very little surface damage. If it was between 5 to 15, you would get some, and if it was greater than 15, you would expect to get extensive surface damage. So in this case, you can see the liquefaction potential index is coming in at around 12 when you sum it up. So it says that you should expect to get some surface damage, which is what they did. So, and the next one is vertical settlements and lateral spreads. But before I talk about that, I really need to go over and say, well, what did we actually input to do all of this? And so there's a little calculation properties button up here. And when you click that, it starts to now give you all the options for the analysis. And the first one is the general one. This is where you're going to choose what calculation method. And of course, it defaults to the NSIR method, which is the Robertson and Ride CPT-based method. But you've got choices. You can use Moss et al. Rob Moss got his PhD at UC Berkeley and was sort of an updated CPT-based method. And then Idris and Bollinger produced their book in 2008, which gave updated methods. So all three methods are in there. But right now, I'll just illustrate it with the NSIR method. And at this State Beach site, it was a magnitude 7 earthquake, and the maximum surface acceleration was estimated to be about 0.28 g. The water table was about 1.8 meters down at the time of the CPT as well as at the time of the earthquake. So you've got the two options here. And the reason you've got two groundwater levels is because when you push the CPT, of course, the water level may be different at the time of the earthquake. And in many regions, California being one, is where you often have to design for maximum elevation of the groundwater table at the time of the earthquake. So it's very common that these could be different. The groundwater table that's input at the time you did the CPT is used to normalize the CPT data, so that normalized CPT values essentially are used to estimate the in situ state of the soil, and then that in situ state is used to estimate the cyclic resistance ratio. And the groundwater table at the time of the earthquake is so that you can determine the effective stress in the ground at the time of the earthquake, which is used to calculate this cyclic stress ratio at the time of the earthquake. I think I made a small error. When I said the in situ groundwater table at the time of the CPT, that's used to estimate the cyclic resistance ratio. And the groundwater at the time of the earthquake is to get the cyclic stress ratio. And you notice that you do have an option if the groundwater conditions are non-hydrostatic, that you can actually put in the non-hydrostatic. And of course, you can have a non-hydrostatic at the time you did the CPT, and also possibly still having one at the time of the earthquake. So you've got an option to input that with a little table, just input how the pore pressure, the piezometric profile varies with depth, and then you've got a little option to duplicate it for the earthquake as well. We're not going to do that. The groundwater conditions are roughly hydrostatic at this Moss Landing because it's close to the ocean. So it is pretty well hydrostatic. And that was confirmed by the CPT. And then under assessment parameters, so depending on what method you use, so it says if you chose the first one, so you've got the basic NSIR method, and it says if you're going to stick with that, you can sort of just confirm, are you going to do all the elements of it, which is stick to the stress exponent as defined by Zhang, or actually use the way it was defined by Yao et al., which is a slight difference. And then are you going to set a limit to the normalization, often set at 1.7? Are you going to use the IC cutoff at 2.6, the boundary between soils that are more sand-like to soils that are more clay-like, which was suggested as the boundary? And the reason you have to define that is because the NSIR method applies only to sandy soils. And so you need to define what's the CPT cutoff that defines sandy soils. And then whether or not you're going to apply the K-sigma overburden correction. And then you do have the option here to choose the sort of the updated NSIR method. This is the one I updated in 2009. And the update is essentially where I updated the stress exponent. I sort of increased the CN limit to 2, and I dropped the K-sigma because I'd updated the stress component, and it varies with stress. The stress exponent itself varies with effective overburden pressure. Then you don't need the K-sigma. And the other big difference is when I updated it, I included clay-like soil. So there's no IC cutoff. So when you use the 2009 method, it'll go from sand-like to clay-like soil and capture, liquefaction in the sand-like and cyclic softening in the clay-like soil. So it'll do it uniformly. Now it's got two little boxes under here because if you use this method, then in the clay-like region, you need to define the limits of volumetric strain and shear strain. Because in the sand-like region, that's done automatically based on all of that lab testing of sands. But in the clay-like region, you can't use that, so you have to sort of define the limits. And the program defaults to a relatively small amount of volumetric strain in the clay-like soils, and this actually should be 4% for the maximum shear strain. Now if you selected the Idris and Bollinger method, then their method also requires you to define a few things, and one of them is that they like to use fines content to make the correction, and so you can either use measured values or you can use the relationship that they had suggested in their book, which was based on a simple formula that had an alpha and a beta, or you can have a user-defined one where you can actually input your, it says unit weight, there's a small bug there, it should say fines content. You can actually input the fines content and the program will calculate the equivalent values, or you can use the Robertson and Ride fines content relationship. So you got a choice. You can either use my original apparent fines content correlation, or the one that was in the Idris and Bollinger book, which is pretty similar except at the low fines content range, or you can input your own user-defined one. And then with the Idris and Bollinger method, you also have the option to add in the clay-like behavior as well, and you've got options of how you do the settlement and etc. I'll come back to that later. Then under advanced parameters, there's quite a few extra things to do. One is, do you want to look at every data point, or do you want to do a little bit of averaging? It depends on the frequency at which data is collected. But quite often, if it's collected at a reasonable frequency of, say, every 2 to 5 centimeters, then you can look at every data point. If it's collected at very high frequency, sometimes a little bit of averaging can help. This is where you put the cone net area ratio to get QT. You can limit the depth. So in Japan, it's quite common to limit it at 15 meters. And sometimes you might want to do that if you've got very deep CPT soundings, to not be too conservative and capture too much liquefaction at depth. But one of the nice things, as you'll see, is you can select and unselect this one and then see what the influence is. And then you can automatically estimate the unit weight, or you could input an average unit weight, or you could input a table of unit weights with depth. And you can see that there's some numbers were put in. These were the numbers that Idris and Bollinger used in their book, because this is actually the profile in their worked example in the book. So you've got the option to go with those numbers. And then up here, this is that K-sigma correction. This is the auto transition layer. So in this particular profile, it is mostly clean sands. If I go back here, you see it's mostly clean sands, but there is this clay layer. So right at the bottom of the clay layer, there's this transition from the sand into the clay layer, and then transitioning back from the clay layer back into the silty sand below. And so you can see I've identified the transitions here. And you've got the options to identify them and exclude them from the analysis. And if I go to the liquefaction plot, you see that that transition is basically at 8.5 meters and at 9 meters. And so you can see that they've been excluded. If I go back and deselect that auto transition and say OK, you'll see them just pop back in. If you just look at this region here, you'll see them come back in. But yeah, see, so that transition layer got added back in. And you tend to see it's a little bit conservative if you get too many of these transition layers. So it's often nice to remove them to avoid that excessive conservatism. But the nice thing with the software is you can try it both with and without and see what the effect is. You saw that there were some transition layers at depth as well. So below 11 meters here. The data sort of transitions right from sort of silty sand to clay, and there's a bunch of little layers in there that get caught right at that transition zone. So let's go back. We're still working our way through. We've got the advanced parameters. There's a bunch of other little features in here. It's hard to go through all of them, but they're designed to give you sort of options to fine-tune it. And maybe I'll come back to some of these features a little bit later and exactly how they work. Site conditions, whether or not the site has changed, whether or not you're going to add fill between when you did the CPT and when the earthquake occurs, you have the option to add that extra bit on. Or if you're going to make an excavation, sort of excavate and maybe even put in a footing. So if you're going to excavate and put a footing in, you want to see what the effect of that has on the overburden and the potential for liquefaction. You can do that. But in this particular case, site conditions weren't changed, so there's no fill and no excavation. And then if there is sloping ground or a free face, you've got the option to put that information. And here it was essentially level ground conditions at the roadway and then gently sloping into the harbor. And so these are sort of approximate numbers. The height of the free face is estimated at about 5 meters, and we're about 40 meters back from the toe of that sloping area. And I've selected to ignore displacements below twice the height of the free face. So below 10 meters, in this case the height of the free face is 5 meters, so I'm ignoring anything below 10 meters from the ground surface. Well, so lots of features there. And so that's what we had used. Essentially that's what I had shown before, and that's what you're seeing here. And so you can see that the basic NCO method predicts it pretty well. It's predicting liquefaction occurring in that upper clean sand, roughly from the water table at 1.8 down to about 5.5 meters, and then very little liquefaction below, a little bit down here at 10 meters in that silty sand. You got this clay layer, then a sand, and then it sort of transitions into silty sand into the clay below, and it's sort of predicting a little bit of liquefaction down there. But if you come to the vertical settlements, this is where it sort of gives you some maybe greater insight, because Zhang's approach was to calculate the factor of safety and then using the Ishar and Yosemite lab data and clean sand equivalent estimate volumetric strains and then sum those up. So you see this nice little plot of summing the settlement up with depth, and so there's a little bit down at 10 meters and then essentially not very much up until you get to 5 meters, and then of course most of the settlement occurs at 5 meters. So it's predicting a post-earthquake settlement of around 13 centimeters, with most of it occurring in that upper clean sand and just a little bit, a few centimeters right at the bottom there. And with the lateral spread again, very little at the bottom, and then most of it occurring in that liquefied clean sand in the upper portion. So actually the prediction using the NCO method is pretty similar to what was observed. And of course you've got the option to look at how sensitive this results are. So the program's got a couple of nice features. One in particular I like is that there's a little button up here that allows you to do a parametric analysis. And what it does is it says that you can see how sensitive the results are to variation defaulted. So maybe we'll change it from 0.1 and we'll go all the way up to 0.5 to sort of show the extreme, and a magnitude 5 earthquake up to a magnitude 8.5. And we'll just look at the post-earthquake settlements, those vertical settlements. And when you click calculate, what it does is it calculates all of those settlements under all of those different combinations of surface acceleration and magnitude, and it presents this little surface. And it shows you the value for that design one that we had selected. We had selected a magnitude 7 earthquake and 0.28, excuse me. And so that was the design earthquake that we were using. And what it does is it shows you how sensitive that calculation of settlement is to changes in the earthquake. Because often, of course, if you're designing for a future earthquake, you often don't know exactly how big that earthquake is going to be at your site. And so you want a sense of how sensitive are the results to that assumed design earthquake. One of the nice features, you can actually move this little plot around and look at it from different angles to decide which is your best way to see that. And you can play around with the range over which you look at it. But you can see it's intuitively it's nice. It says that, of course, if the earthquake was very small, there would be no liquefaction and no settlement, of course. But then as the earthquake gets bigger, either the surface acceleration or magnitude, then of course liquefaction starts to occur. And then of course rapidly it will occur and you get large change in settlement. But then eventually it caps out. So when the earthquake becomes very big, you're essentially liquefying everything that is going to liquefy. And there's only so much volumetric strain can occur. So if the sand is very loose, you can only densify it so much. And so of course the volumetric strain caps out. So that's a very sort of nice, insightful way to see how sensitive your analysis are. And so if for your design earthquake, if your design earthquake is up in the region where it caps out, then you know the results are not that sensitive to the earthquake. But if your design earthquake is right in this region where there's maximum change occurring, then you know that the estimate of both liquefaction and resulting deformations are very sensitive to the earthquake. And so small changes in the earthquake will make a big difference in the estimated post-earthquake deformations. And so you need to keep that in mind when you're sort of trying to estimate what the damage would be. Another way to look at that is John had added a feature up here where some users have said, well, could I just look at the influence of the peak ground acceleration on the, for example, settlements? And could I compare it for several of the soundings? So here I've got like UC 14 and 16 are selected here. So when I do this feature, it's going to look at both of those two. So here's UC 14 to 16. Remember, 16 is a little bit further back and a little bit denser. And so when I perform the calculation here, what it shows me is here's the settlement against peak ground acceleration. So UC 14, of course, it's quite loose. It liquefies quite early, rapidly rises up, and then begins to cap out. Remember, the design earthquake is around about 0.28 here, so it's right about here. So you can see that we're in the portion where it's beginning to flatten out, so the results are not that sensitive to the size of the earthquake. And down at 16, this is just where it begins to liquefy, and so obviously the settlements are a lot smaller, and because it's denser, it's less sensitive to the size of the earthquake. You see that the settlements are not overly sensitive. So that's quite a nice feature, particularly useful if you've got lots of CPTs. If you're comparing 10, 20, 30 CPTs at a site and you want to see which are the worst ones, which are the loosest locations, and which are most sensitive to ground acceleration, and this is a very nice way to do it. You know, for example, if I add in a couple more, you'll see it. See, now I've got 4 here. You get to see the sensitivity of all of them. And I'll just deselect those 2 again. There's also a feature where if you've got multiple CPTs and you want to identify which are the worst ones, and you can look at an overall report and you get to choose what you want. You can look at liquefaction potential index or settlement or lateral displacement or probability of liquefaction. I'll come back to that in a second. So if I select vertical settlements again, then it shows me a little bar chart. Here's UC 14 and 16. Now for only 2, of course, it's not that interesting, but if you had 20 or 30 CPTs, it's a very easy way of doing a quick check to determine which are the loosest. And because of the different methods, some people like to compare the different methods. So here's with those UC 14 and 16, you can compare the different methods. So you've got the original NSEER method, then the updated one, and then Idris and Bollinger's, and then Moss et al. So you can look at vertical settlements, and if I do the calculation, it gives you this little bar chart for those 2 CPTs, and it compares the methods. So the red is the original NSEER CPT-based method, which is focused on sands only. The green one is the little bit of updated where it transitions and includes softening and clays. You can see not much difference there because this is mostly a clean sand site, and the clays don't liquefy or don't soften very much. And then here you see Idris and Bollinger a little bit more conservative, and in this particular case at UC 14, Moss is a little bit more conservative, but not so bad at 16. So you can get to compare the different methods, and you can cut them out, so you sort of exclude ones you don't want to look at, etc. So you get to play around and compare them. So that was a quick overview of how the basics of it work, and if I come back to the liquefaction curve, so here it is for UC 14, and there it was for 16. You can see less liquefaction, less deformation. So if I switch over to UC 8 now, UC 8 was at, I'll just flip back to the slides here. UC 8 was at the marine lab where a lateral spread occurred. This is the picture of the lab. This is from Harder, showing the extensive lateral spreading and damage to the building. And this was the profile. And the difference at UC 8, if I go back to the basic CPT profile, so here's the basic CPT. Ground conditions more varied here. You can see that there's some sort of interbedded fine-grained soils down to about 3.5 meters, then a sand layer, clay layer at 6 meters back into the sand, And then from 7 down to 10 meters is a silty sand region. And you can see the cone profile is lower, friction ratio is higher, sort of up around 1 to 1.5%. Pore pressures, a little bit of positive, a little bit of negative relative to hydrostatic, and so on. So a little bit more complex profile. But the layer that was considered to have liquefied was this silty sand layer, roughly between 7 to 10 meters, 7.5 to 10 meters. So if you look at the analysis, again, let's quickly go through it. This is choosing the NCA method, not doing anything special to the analysis. And so you can see that it's essentially very little liquefaction predicted in the upper 7 meters, and then liquefaction is predicted roughly from 7.5 down to 10 meters here. And because of the interbedded, it's probably more important to remove all of these transition layers. So you can see here, here's the sand layer. So when you go from sand into clay, there's a transition layer and then back out again. Program's not always able to capture the transition coming out of a thin clay layer. So it's not perfect, but it does capture quite a few of them. So you can adjust how aggressively you go for those. That's under the advanced parameters. So when you tune it, you get to play around with how aggressively you want to try and identify these. You can look at the rate of change of IC, the number of data points, and the region over which. So you can see if I do it more aggressively, I can capture that transition layer coming out. Let's do that. Apply that. Recalculate so it did capture that transition layer coming out. So what you can do when you go to the liquefaction, often the settlement and lateral displacement are the ones to look at, or the liquefaction potential index. So here it's saying that it's predicting about 7 centimeters of settlement, and with the geometry here, fairly large lateral displacement of about 170 centimeters, so over a meter of lateral displacement, which is pretty similar to what was observed. But if you want to see the influence of either including or excluding the transition layers, you just go back to that tab, deselect it, ask it to recalculate, and see what the effect is. And you can see that the settlements, of course, went up, and the lateral displacement went up quite a bit. And it shows up on the cyclic stress ratio, cyclic resistance ratio plot, where now you see lots of little areas getting pulled underneath. And because of the transitions, you've got zones being pulled in, and then, of course, when it hits a clay, it says it's not liquefiable, and then the transition comes back in. So when you see this highly variable profile, if you go back, so like from 3 to 4 meters, from 3 to 4 meters, you can see that this is sort of an interbedded sands and clays up here. So you can see that if you don't exclude them, you end up picking up all these little bits of liquefaction. And it has, in this particular case, it has a fairly major effect. So what was it, about 16 centimeters of settlement, keeping the transition layers in, but if you remove them, I think it dropped down to about 7. See, yeah, it dropped. So a fairly significant effect. So you know, obviously when you're looking at a case history, you've got the observation to go on to guide you. But when you're designing for a new one, you have to use judgment about how you think those transition layers may influence the result. And so clearly you have to use your judgment. But the program's designed to at least present you the options so that it can guide you on how to make those judgments. At Moss Landing, again, you can look at the sensitivity. Oops, let me go back. Select it. Sensitivity to the peak ground acceleration. And remember, we looked at 14, it was very sensitive. 16 was denser, it didn't. At UC8, this middle one, and you can see that the design earthquake's about 0.28. So you can see that at least for settlements and lateral spreads, the amount of deformation is not that sensitive to the earthquake, because essentially it was pretty loose. That silty sand was loose, it liquefied fairly early, and then not being influenced too much by the size of the earthquake. Okay, those are quick reviews. You do have an overlay button where you can overlay them. So here I've got the 3 selected, 14, 16, and 8, and you've got the basic plots and the cyclic liquefaction plots, so you can compare what they look like. That's useful when you've got a site that's got multiple CPTs and you want to get some sense of how things are varying across the site. The program also has a module. If you have SPT data, I'm going to go back to UC14 because there is some there. If you've got SPT data, you can run a companion SPT analysis. There was an adjacent borehole next to UC14, and so here was the measured flow count. So you can input them in, and the unit weights and the fines content. And of course, if there's clay layers like this little layer here, whether or not it's considered to be liquefiable, what method you want to use, the type of SPT sampler, the energy level, etc. And then it presents you the results, and we'll show you the data on the CLiq stress ratio versus SPT N160 clean sand equivalent plot. It shows the NCR line, and then it shows you the SPT blow count, both the measured ones, the normalized N160, and then the N160 clean sand equivalent. And then it shows you the CLiq resistance ratio. So the blue line is based on the SPT, but of course, since it is a CPT-based program, it does show the CPT one in the background because there has to be a CPT profile for this portion to run. So it's a way of comparing the two. And you can see that actually, in this particular case, they compare quite well. Both of them would predict liquefaction roughly from 2 to 5 meters, and then maybe a little bit again down at 10 meters. So if you've got SPT data, you can compare it. And likewise, if you've got shear wave velocity data, you can compare it. You can add that in, get similar plots as well. There isn't any at this location. Maybe I'll just pop back to the slides to remind myself about what we want to talk about next. Oh yes, I just maybe mention about Kornblum. In part one, I did mention about Kornblum because Kornblum was an interesting case history. But if you look at the cone profile, it's very varied material. It's mostly silts and silty clays with some sand layers. There's a sand layer down around 10.5 to 12.5 meters, and then back into bed. So it's quite a complex site in terms of very variable and high fines content. So it's a test of the fines content, and so the data plots well down the chart, close to this IC of 6. But what was interesting about it is that it experienced 2 earthquakes. So there was an earthquake in 1979 called the Imperial Valley earthquake, and it was a magnitude 6.6, 0.13 G surface acceleration. So that calculates to have a CLiq stress ratio of slightly under 0.1, so 0.08 to 0.09, and no liquefaction observed, and there were 6 CPTs. I'm only showing one of them, but there were 6. And then a few years later in 1981, another earthquake occurred called the Westmoreland earthquake. It was a slightly smaller magnitude earthquake, but it was actually closer to the site. The source was closer, so the surface acceleration was higher at 0.19 G, so the calculated CLiq stress ratio was a little bit higher at around 0.1, so 0.09 to 0.11. And liquefaction did occur. There were sand boils, a little bit of surface movement, and it was a silty sand. In the presentation, I showed where the data plotted, so that the measured values are there, and then you correct the data over, and the 2 data points are very close to the boundary line. And I showed that the methods gave slightly different answers. So we'll maybe go back and illustrate that. So if you look at the liquefaction, so you can see here, I think, if I can remember rightly, so this is the larger one, yes, with 0.19 G. So this is the Westmoreland earthquake, where liquefaction did occur, or was a little bit occurred. And so you can see that you're just predicting that these little sandy regions where it's a factor of safety very close to 1, little bit of settlement predicted a few centimeters. And if I go back to the slide, so so the Imperial Valley earthquake, essentially predicting very little earthquake. And this is the one we're looking at here. This is the CPT one that's referred to just as Kornblum. And the Idris and Bollinger method predict larger settlements, and Moss a lot larger. This is obviously for the one where it didn't liquefy. If I go back, maybe change that over to 0.13, and you'll see So the cyclic stress ratio moves over a little bit, the factor of safeties get a little bit bigger, the settlements essentially disappear. A couple of other features. I'm just going to show this Treasure Island one. So Treasure Island is an island in the Bay Area. It did experience some liquefaction in the Loma Prieta. But it's got mostly, it's an island, so it was sand fill over San Francisco Bay muds, and so you got this loose sand over bay muds, and so you can see the friction ratios are low in the sand, and then where the bay muds are is high, and pore pressures are high in the bay muds. But what I wanted to illustrate is that the program has the ability to look at softening in clays as well. So here, if you just run the basic NSEER analysis, so the basic NSEER, which only looks at sands, then this is what you get. It predicts liquefaction in the upper loose sand, and of course nothing anywhere else. And it predicts a fair bit of settlement and some lateral spread. But if you want to try and add in, you can use the updated method that tries to include clay-like soils, so there's no cutoff. So now if I run the analysis, you'll see now you get a cyclic resistance ratio predicted all the way down. It's a continuous profile, so it's not excluding anything. And so in the clay, in the lower young bay muds now it's predicting, it says the cyclic resistance ratio to resist softening is just a little bit higher than the earthquake produced. Now what it sort of illustrates is if the earthquake were bigger or closer, so that the cyclic stress ratio is larger, one could expect some cyclic softening in this young bay muds. And so you can see here with the volumetric strain, although its factor of safety is a little bit larger than one, just a little bit of volumetric strain being predicted, and essentially no shear strain being predicted. Well, partly because the height of the free face, twice the height of the free face, only went down to 10 meters. I have another example here. This is actually of a dense sand, a dense, relatively clean sand. This was published by University of Michigan, and they refer to it as their Griffin site. It's a dense, it's got some looser sand in the upper few meters and then a pretty dense sand. So you see much larger cone values, much higher normalized cone values. And I put in a sort of a design earthquake just to sort of illustrate that it is much denser. The cyclic resistance ratios are generally larger. One of the things I didn't show is that there is a tab at the bottom, so you've got these intermediary parameters that steps you through each of the components, and then the liquefaction that shows you the results of the analysis. And then this one, it just shows you the normalized soil behavior type, and it shows where the data plots on the chart. So at this site, dense sand plotting high up. If I go back to, for example, Treasure Island, and we look at this chart, you can see that you've got the loose sand plotting in the chart, and then here's the young bay mud, and the Moss Landing, you see 14, mostly relatively loose sand, clean sand plotting up there, a little bit of clay down here. Okay, and then maybe the next one. So that sort of walked through cyclic liquefaction and how you can run the analysis using the software. So some of the nice features is you do get to control most of the variables. So under these advanced ones, I touched on the main ones, but there are some other ones down here. You can vary the cutoff. So for example, if you have a soil, let's say you have a stiff silty clay. So let me go back to the chart. So a stiff silty clay, here's the normalized soil behavior chart. So a normally consolidated clay would plot down here, like you saw with the young bay muds. But the stiffer it gets, it plots higher and higher. Then eventually, if it's a very stiff clay, it may actually plot just up here, still in zone 4, meaning it's a silty clay, but because the IC doesn't match exactly the zones, then it has an IC less than 2.6. And so if the data is being caught in that area, then of course the program is going to assume it's a sand-like material, and then we'll calculate cyclic resistance ratio. But if you've taken samples and you've determined that these soils are plastic and they're not susceptible to liquefaction, then you do have the option to adjust the IC cutoff. So in this particular case, you could make it smaller. So you would cut off that stiff clay and avoid it getting caught in the calculation. So you can see if I change that number to 2.4 and then press OK, you'll see the line gets moved over. It shows the original 2.6, and then the red line shows where you've moved the cutoff. So if you had data in this zone 4 here, stiff, silty clay, it's clearly a clay, so it's not susceptible to cyclic liquefaction. But it has an IC just less than 2.6, then you have the option to cut it off. Likewise, if the reverse is true, if you've got a silty sand or a silt that's plotting with an IC greater than 2.6 and you want to include it in the analysis, then likewise you can adjust that to a value greater than 2.6. Here's this limit on the normalization. NCER limits it at 1.7, but you can adjust it. You can also put in a user-defined factor of safety if you want to, for design purposes, put in a factor of safety slightly greater than 1. I'm not a big fan of that, but some people do like to do it, so you do have that option. You've got the option to, if you've got a water table relatively deep and you've got several meters of loose dry sand, you do have the option to estimate the volumetric strain in the dry sand due to seismic compression and add that in. You've got the option to customize the cyclic stress ratio, so if you don't want to use the simplified NCER approach, you may have done a site-specific seismicity analysis and calculated the cyclic stress ratio with depth. You can add that. And then some of these features down here are sort of advanced features that are becoming more popular, and this one is an interesting one, which is weighting the volumetric strain. So let's go back to UC 14, for example. And most of the settlement is occurring from 2 to 5 meters and a little bit down to 10 meters. But for example, there are some advanced parameters. So here I limited it to 50 meters. If I take that limit off, you'll see that there is a little bit of liquefaction occurring at depth. It's off the plot here. I'd have to change the scales. But it's down at around 20 meters. There's a little bit of liquefaction. And so you've got various ways to handle that. You can sort of limit the analysis depth, which would cut it off completely, or you can put a weighting, which is it's built on the Iwasaki approach that says, most of the damage, particularly on shallow foundations, is due to liquefaction that occurs close to the ground surface. So Setin has suggested, the Setin and Al had a paper in ASC where they had suggested this concept of weighting the volumetric strain. So if you select that, they had suggested 18 meters. You can adjust that number. But if we stick with that recommended 18 meters, what it does is does a linear weighting. It weights it at a value of 1 near the surface and then 0 at 18 meters. And so, linearly weights it accordingly. So now you'll see here we're predicting about 15 centimeters with no weighting. So if I click OK, it now weights it with depth, and you can see that it's weighted the deeper one and almost removed it all, and has moved the vertical settlement over from 15 down to about 9. So if you've got a building on shallow foundations, that is a way of adjusting the calculated volumetric strains, because of course the calculation in a way doesn't know the depth at what it occurs. It just says, hey, liquefaction is going to occur, and it's got a sort of certain approximate relative density, and it's estimated volumetric strains and just sum them up equally. So it's treated them all equally. So this is an option to not to treat them equally and actually weight them as a function of depth. So that's quite a nice little feature. I think that's a feature you're going to see probably more of in the future. There's also a feature that if you have older soils, so if you're in a geologic region where you know that these sands are older and we know that Pleistocene sands are more resistant, you do have an option to add in an aging factor. So you multiply the cyclic resistance by this aging factor. I mean, it says 0 there, but essentially it's 1. And so if you've got Pleistocene materials and you think they're 10 or 20% stronger because of that age, you've got the option to do that, and you can actually vary it with depth. Again, there's a little typo here. It says unit weights. It should say aging factor. Ron Andrus at Clemson University, he's done some work by looking at the measured shear wave velocity compared to the estimated shear wave velocity for very young sands, and using that ratio of the shear wave velocities measured to estimated to give you a sense of this aging factor. And then these numbers over here, the NKT factor, is if you are looking at clays and you want to estimate CLiq Software, then that is based on the peak undrained strength, and so you can vary what NKT value is used on that. There's also a little button down here where you can also adjust the volumetric strains based on probabilities. Let's go back to this. You saw this plot of factor of safety. If I right-click on this plot, I have the option to switch the plot to a plot of probability. So instead of factor of safety from 0 to 2, I can look at probability from 0 to 1 or 100%. So you can see it's almost like 100% probability that that upper layer is going to liquefy, and the other ones is almost 0% probability. But there are sort of layers here. You can see factor of safety just touches 1, but the probability of liquefaction is maybe around 30%. So that's sort of an alternative way of looking. Rather than looking at factor of safety, you can look at probability. It's quite a nice feature. So you can see there's quite a number of advanced features in there. So in essence of time here, I want to just quickly jump on to, well, what do I do about potential for flow liquefaction? So here I'm going to jump to a different case. So this is Jamuna Bridge. So you see a much, much looser. So the scales haven't changed. So you notice the scales are the same. If I go back to UC 14, you can see that the tip resistances are up around 10 to 15 megapascals, where at Jamuna it's much lower. Free draining sand, so this is a micaceous, loose, clean sand. So it didn't have an earthquake, so I have put one in, but it would show the extensive liquefaction even for a relatively small earthquake with very large deformations. And putting in the geometry they had there, you see lateral deformations of 5 meters. So it's clearly a warning to say, wow, even looking at cyclic or seismic liquefaction, I'm predicting very large lateral displacements. I need to check whether or not there's a risk that I could get strain softening here. And one way to do it is to look at the data on the chart. And so here was the IC of 2.6 that divides sand-like to clay-like materials. And this other curve was essentially the line that would distinguish dilatant materials from contractant materials. So in this particular case, it's a relatively clean sand, and a significant portion of it is falling below that boundary line between dilatant and contractant. So although it's a clean sand, it's very loose, it's contractant, and so potentially strain softening. So this last tab on the bottom is how you check for that. Check for strength loss. So here's the normalized cone resistance, here's the sort of fines content correction, and then here's the clean sand equivalent. I'll just change the scale a little bit to 200 to blow it up a little bit. And you see the red portion. This red portion is wherever the clean sand equivalent is less than 70. This curved boundary line is essentially the contour of a clean sand equivalent of 70. And so you can see that much of the data falls below that clean sand equivalent of 70. And so that's predicted to be contractant and potentially strain softening. And so the program calculates a liquefied undrained strength ratio here in red. Now if I change the scale, you'll see that it also shows the peak strength. So the black line is sort of the estimated peak undrained strength ratio. And what that does, of course, is if it was a clay, it would base it on the peak undrained strength. If it's a sand, it's basing it on the estimated friction angle. Sorry, the scale's changed on me there. Depth scale. And so it's based on the peak friction angle, and the red line, of course, is whenever it drops below that clean sand equivalent of 70 and considered to be potentially strain softening, it then goes into that relationship of liquefied undrained strength ratio. And of course, if you use a different method, so for example, if you used Idris and Bollinger's method, it uses their approach for liquefied undrained strength, and so you'll see that number will change. There, see, it's modified the liquefied undrained strength based on Idris and Bollinger's approach. So you can see when you start to get into the examples, time can whiz by pretty quickly. One last thing to touch on, across the top here, there's one more tab that says 2Ds. I don't have time to to go into it in much detail, but this is a very nice extra feature. If you have a site that has multiple CPTs, you can actually create a two-dimensional plan, and so you can either assign coordinates to each of the CPTs or drag and put them into the plot, and they pop into the plot using some of these buttons up here. And then when you click to contour it, it actually contours in this. You can either do liquefaction potential index or settlement, and so you get a nice 2D contour of the site using whatever method you had selected and whatever features you had selected, and it will contour it, and you get a nice color or black and white 2D contour of the estimated deformation. So that's a very nice extra feature. Okay, so we covered a lot of ground. I know I had to move fairly quickly. I apologize for that. If I come back to the slides, just remind myself if I missed anything. So the slides just reiterated some of the main points. So that concludes the main part. I apologize if I went a little bit fast on some areas, but hopefully you got a reasonable idea of what's going. And before I actually get to the questions, Kelly reminded me that we will give away up to 10 free licenses for CLiq, and John's very generous. John Ioannidis, geologist Mickey in Greece, has been very generous and said that we can give away some licenses. And so to do that, what we'll do is the first 10 people that email Kelly, so frantically look up what Kelly's email address is, or then, so the question is what is the soil behavior type IC cutoff that's recommended as the boundary between sand-like and clay-like behavior? What number is typically recommended for that cutoff, particularly in the NCER approach? So if you know the answer to that, email it to Kelly, and the first 10 will get a nice free license for CLiq, and hopefully you'll enjoy using it. And remember how to pronounce it. It's not CLiq, it's CLiq. Okay, so Kelly's written down a couple of questions, and I think the first one says, CLiq seems to often yield lateral displacements, either a few meters or a few feet, even for relatively flat or gently sloping ground, no open face. Is this assuming a superficial fissure or lateral displacement in the liquefied zone? Okay, so good question. If I go back to the software, let's go back to UC14 as our example. Oh, see, that froze on me. It's whenever you switch between PowerPoint, when PowerPoint is actually open, that's what does it. What happens is you have that feature of where you put in the ground geometry. If you actually put in level ground conditions, then of course you'll get zero lateral displacement. So if you tell it it's level ground, there is no shear strain, so the program calculates zero lateral displacement. However, if you put in gently sloping ground, so if you choose that it's infinitely sloping ground and you put in a small percentage, then the program sort of defaults that it's infinitely sloping. So it's sloping infinitely in both directions, and that the shear stresses go sort of infinitely in depth too. So you get a little liquefied layer down at 10 or 20 meters, it's going to assume that that's going to generate lateral displacement. So it does tend to be conservative. It's often better to put in the sort of level ground with a free face, because that then sort of defines limits to it. And of course you can then click that button that says, well, assume that no lateral displacements are generated at a depth greater than twice the height of the free face. So it is a little bit of catch in the system that if you choose the gently sloping ground, small little bits of liquefaction at depths tend to get overestimated in their importance to the contribution of that lateral spread. So you have to use your judgment. And the nice thing about the program, it is always showing you the profile, so it's showing you the depth at which layers are liquefying, and so hence guiding you on how you can try and adjust the results. So you can see liquefaction's a lot more complicated than just basic interpretation of CPT. There's a lot more variables, requires a lot more judgments. So we've tried to design the software so that it gives you the options to adjust some of the variables in an effort to home in on what you think is the correct answer. Next question. For the companion SPT liquefaction screening, is it possible to modify the CLiq resistance ratio based on OCR? Well, in clean sands, that's tough. I mean, the NCR method does not give you an option to adjust the CLiq resistance ratio in sands based on stress history, often because it's hard to know what the stress history in clean sands are based on either SPT or CPT. So no, the program doesn't have a way of adjusting stress history either based on CPT or SPT. You can cheat the system a little bit. You saw that on the CPT side of it, there was that aging correction factor. And so if you felt that you knew that there was some stress history and you felt that that contributed to an increase in CLiq resistance ratio, then you could put in like a pseudo-aging factor to put in a 10 or 20% increase in CLiq resistance ratio in an effort to help you do that. Next question is which VS method does it use? It gives you a choice. You've got options, and of course, since I can't get the program to wake up again, it's not letting me show you that. Oh, here we go. Let me reopen it. With luck, I'll got to show it to you. Here we go. So I'll reopen the program. Load that file in again. So here we are, UC14. So here's the shear wave velocity. Note you got a choice of methods. See over here on the right here. So NCR, the original NCR publication by Yao et al. Did include a shear wave velocity method. It was based on Andrus and Stokes' method back in the late 90s. Well, just recently, Kay and al., quite a number of authors, did a very nice study, recently published in the ASCE, where they went to a lot more sites, really increased the number of case histories. And so they've sort of created an update. And so actually, I've got to actually tell it to calculate to do that. Yeah, there we go. So here's the CLiq stress ratio against normalized shear wave velocity. Here's Kay et al.'s method. You see now it extends out to almost 250 meters per second for very large earthquakes. So we just tag in on that number. It's 240 meters per second at 0.6, whereas the original NCR one went almost asymptotic. If I flip back, yeah. So here you can see the original Andrus and Stokes essentially maxed out at about 210 meters per second at 0.6. So you can see KN has sort of moved it over a little bit at the upper end. It's essentially quite similar in the low end. So yeah, you've got two choices of the shear wave velocity method. Okay, last question. Is strength softening calculated only for the clay-like soils? No, that's a good question. So if you look at that Jamuna Bridge example, this is all clean sand. There's no clay here at all. It's all basically a uniform, micaceous, clean sand. And so when you went to the check for strength loss, it's calculating a clean sand equivalent. Let me just, I'm going to choose the NCR method, just a small detail here. So you see when I choose the NCR method, you can see that the fines content correction is sort of predicting it to be because it's such a loose sand, it's sort of predicting it to be slightly silty. So there's a small KC correction slightly bigger than 1. But you can see that it's predicting the liquefied undrained strength most of the way down. Now, every time it bumps up, so this little denser layer here, where the clean sand equivalent is now greater than 70, it of course goes to the peak undrained strength ratio based on friction angle, and then below that where it's looser, it's predicting the liquefied undrained strength. So no, it's not limited only to clay-like soils. How the program does is if you've got an interbedded profile, that's a mixture of clays and sands. So I'll switch, say, to UC8, which have a mixture of sands and clays. Maybe I'll go back to the basic for what you see here. So you got clays and sands intermixed. So if I go to the, whoops, check for strength loss, maybe go to the analog. So full range of soil deposits at this site. You've got some sands up here, silty sands, and some clays. So when you check for strength loss, for example, here's a clay layer here down around 11 to 12 meters. High fines content correction, but the clean sand equivalent is still low, and it's predicting, you see, only little bits of strain softening, not all of that layer. And how it's doing is it's treating it as a clay, and so it's saying how sensitive is that clay, and it's estimating the peak strength from the tip resistance and the remolded strength from the sleeve friction. And so the black line is based on the peak undrained strength from the tip resistance. The red line is the remolded strength in the clay. So that's how it does it. So if it's a clay layer, it calculates the remolded undrained strength ratio, which is not strictly the liquefied undrained strength ratio, but it's to guide you that there is a risk of strain softening in the clay layers. Hopefully that answered your question. So Kelly's got a few more questions here. Next one, comment on the selection of groundwater table before and at the time of the earthquake. Often they select earthquake groundwater tables as half a meter less than the regular groundwater table. But in cases like Christchurch, water and sand boils were ejected at the surface. Putting groundwater table at 0 is detrimental to the analysis. Using groundwater table that's like half a meter down seems arbitrary. Yeah, I mean, you don't want to use arbitrary numbers. Obviously, the groundwater table you use for the CPT. So let's go back again to UC14 as an example. It's a fairly good site. So here's the cone data. So tip, frictional ratio, pore pressure. You can see that in the upper clean sand, it's essentially hydrostatic. So if you extrapolate that back, it clearly shows that the water table is close to 2 meters down. It's 1.8 meters down. So you're clearly able to determine what the water table at the time of the CPT is. And of course, hopefully, if you did some dissipation tests, that would help. And of course, a dissipation test in this upper clean sand, it's free draining during the cone, so it quickly confirm what the piezometric head is. Now, the groundwater table at the time of the earthquake, in this particular case, this was a case history where there were some estimates of what the groundwater table was at the time of the earthquake. And at this particular site, this is a harbor right next to the ocean. So at the time of the earthquake, they knew what the tide level was. Tide levels don't vary enormously, but they do vary. But so they were able to estimate the depth to the groundwater reasonably accurate at the time of the earthquake. And even for future earthquakes. So for future earthquakes here, you would presumably be relatively conservative and assume that the earthquake occurred at high tide, and so you would put in the maximum water level, since you wouldn't know exactly when it would occur. And a lot of regions often specify that you need to assume that the water table will be at some maximum level at the time of the earthquake. So if you're at a site where groundwater levels could fluctuate either daily, due to tidal variations, or on a yearly cycle from sort of wet season to dry season, then quite often local codes require that you to use the highest groundwater level. Now here in California, sometimes that can appear somewhat conservative, where California has been experiencing fairly extensive periods of drought, and so as well as regions pumping groundwater from underlying aquifers, and so the water table is relatively low to some of the historical values. And so sometimes, the current water table might be 7 or 8 meters down, but they're required to assume that it'll be at some historical level that maybe was only 1 or 2 meters down. So you can see it can have a huge influence on the resulting liquefaction analysis. So you do need to use a fair bit of judgment on what's an appropriate groundwater level, but the program clearly recognizes that you have two. There's the one at the time of the CPT that's used to normalize the CPT that eventually gets you the cyclic resistance ratio, and then the one at the time of the earthquake that's used to calculate the cyclic stress ratio. Okay, next question. What method is used to calculate liquefaction probability? Oh, that's a good question. So fortunately, you know, Professor Yuang and his colleagues at Clemson University, he's done quite a bit of work on probability to liquefaction, and he wrote a couple of nice papers where he took sort of Moss's updated database, a very extensive database, and he applied the different methods. In one case, he applied the Robertson and Ride, sort of the NCER CPT-based liquefaction method. He applied it to that database, and then based on that extensive database, calculated probability functions. And then quite nicely at the end of the paper sort of linked it back and said, well, actually you could approximate it by linking it to factor of safety. And so at the end of the paper he gave a very simple little formula that linked probability of liquefaction as a function of factor of safety for the given method that was used, in that particular case the Robertson and Ride method that NCER adopted as a CPT-based method. And so he had that link. Now Moss, of course, he processed the data in a probabilistic manner, so he automatically had it. And I'm not sure if Idris and Bollinger strictly gave in the same probabilistic manner. I don't recall. But that's how the link is. It's where somebody looked at the database and then ran a probability analysis, but then ended up by linking factor of safety to probability of liquefaction. And so it's nice to be able to switch between the two. Next question. Can 4 to 6 inches of settlement be allowed for shallow foundation design? Typically suggested values are 1 inches. Yeah, now, you know, that's a good question. So quite often get asked, you know, well, how much surface settlement can you cope with for a building? And the answer is, it depends. It depends on the building and, more importantly, on the variability of the ground. So, for example, if you had a site that a relatively uniform sand deposit across the whole site, let's say it's a hydraulically filled, so it's been placed in a fairly consistent way, thick, consistent layer of sand that potentially could liquefy and generate fairly significant vertical settlements. But if the whole site is going to go down, if the whole site goes down 4 to 6 inches, then the buildings will not suffer much differential settlement and may survive quite well, particularly, of course, if the liquefaction is not actually close to the footings. So let's say you've got shallow foundations, they're founded maybe 1 meter below the ground surface. If the layer that's going to liquefy is maybe 5 to 10 meters down, so a fairly significant distance below the footings, so although you might be predicting 4 to 6 inches of settlement, the buildings actually may not suffer much differential settlement and therefore may not notice much of that movement. Now you may have problems on the edge of the site, you know, on utilities, etc., where there is differential settlement. But for the building, it may not affect it. However, if you were to predict like 1 inch of settlement, but if the site was extremely variable, then of course that 1 inch of total settlement could in fact result in 1 inch of differential settlement. And that's why I like that 2D feature. That if you've got multiple CPTs, it'll actually give you some, and you do enough CPTs. So if you've got a site and you've got 4 or 5 or maybe even 10 CPTs across the site, depending on how large the site is, then by running the analysis and then plotting them in this 2D manner, you do get some idea of what the differential settlement is going to be like. And of course, it's the angular distortion due to differential settlement that creates damage to buildings and shallow foundations. And so it'll give you an idea of what that differential is and therefore what the angular distortion is. And if you're building a new building, then sometimes you can talk to the structural engineers and talk about how you can try and design shallow foundations to cope with that level of differential settlement. So there's no set answer of what's an allowable. The other feature to keep in mind is case histories clearly show that if the layer that liquefies is very close to the footing, so let's say the shallow footings are 1 meter down, but the layer that's going to liquefy is from 1 to 2 meters, so right underneath the footing, then of course because the footings are right on the layer that's going to liquefy, then of course the calculations we're doing for settlement are essentially free field settlements. This is where there is no building on the site, so there's no additional shear stresses from adjacent shallow footings. And so the vertical settlements we're calculating are all based on one-dimensional volumetric strains in a free field environment. Now, of course, if the layer that's liquefying is very close to the base of the footings, then those footings are applying shear stresses. And of course, during the earthquake, as that soil liquefies, it goes to zero effective stress, loses all of its stiffness, then those footings will tend to punch down into the liquefied layers. And so although you might be only calculating 1 inch of free field settlements, if the footing is right on that layer, then of course you could get settlements much larger than that on the individual footing that sits on that liquefied layer. And likewise, if the layer that liquefies is close to the ground surface and you get fissures and you get sand ejected, then the sand ejected itself can cause additional settlements around footings. And so you can see it's quite a complex issue, and you have to use a significant amount of judgment to try and go from the basic calculation to what you think is going to happen based on the actual site and the variability of the site and the proposed building plan for the site. Next question says, typical factor of safety used for liquefiable settlement. Well, there isn't a factor of safety for settlement. What it's doing is the method that's used, the program uses Zhang et al.'s method. Essentially what that did is it calculates the factor of safety against liquefaction and then goes into the lab data that was developed by Ishihara and Yoshimine and says that for that factor of safety and for that normalized cone value, in other words, that density of the soil, these were the sort of volumetric strains that are observed in the field, and it just calculates those volumetric strains and then sums them up with depth. And so when you look at that data that we showed in part 1, those curves that Ishihara and Yoshimine developed, they showed that even when the factor of safety was slightly greater than 1, you could still get some volumetric strains. But when factor of safety dropped below 1, very loose sands would give you very large volumetric strains, whereas dense sands would give you rather moderate volumetric strains. Next question, how do you treat cemented soil in the program? Ooh, that's a tough question. The program can't directly handle cemented soil. If the soil is cemented at the time you push the cone, then you'll get a higher cone resistance, and it'll appear to be a very dense, if it's heavily cemented, it'll appear to be a very dense sand, and so the method should work out reasonably well. So, for example, here, UC14, here's this relatively loose, clean sand with an average value of normalized cone value of about 100. And if the sand was cemented, it would plot higher up and maybe slightly to the right. So it would plot up here. So it would have a much higher normalized cone value and, of course, a much larger cyclic resistance ratio. So indirectly it would handle it because the cone data itself would respond to the fact that it's cemented. However, if you're proposing to cement the soil in the future, the cone can't handle it because it's estimating the cyclic resistance ratio based on what the state of the soil is now when you push the cone profile. Hopefully that answered that question. Why does CLiq show larger lateral spreads than observed even close to a free face? Well, it depends, and often the case when people often say, hey, I'm predicting much larger lateral displacements than we saw from the earthquake, particularly recently from Christchurch, where they've got lots of measurements of lateral spread, and they're doing lots of CPT, so they're comparing them. And sometimes they're seeing that the program's predicting much larger lateral spreads than they're observing. And sometimes that comes about if you go to UC8, for example. Now, UC8 was quite a complex profile, clays and sands and clays. And, parts of Christchurch have some fine-grained layers interbedded with the sands. And so this issue of the transition layers. So here you can see that with the transition layers have been identified in red. And so when you get cases like that, it's important to click on that feature that says identify the transition layers, and you can play around with how aggressively identify them. But often what I do is that I'll run the analysis. So for example, I'm going to remove it here. So run the analysis with the transition layers included. You see here they're all included. So you looked at the results, and here's the lateral displacement. I'm going to go out to large numbers so I can see the value. Yeah, so it's predicting over 3 meters of lateral displacement. Let's just change the scale a little bit to make it a little bit better. So about 3 meters of, oops, extra zero that I didn't need, that's all right. 400 centimeters, that's 4 meters. That's the scale it's going to be plotted. So it's predicting a little over 3 meters of lateral displacement. And you see all these little bits getting captured as liquefied. So it says, okay, 3 meters of lateral displacement, but if I now identify and fairly aggressively have identified these transition layers and say, okay, now let me see what happens if I remove all of them. What happens? You see the lateral displacement jumps from 3 meters down to 1.6, so half of it. It just by removing those transition layers, we remove half the lateral displacement, and of course roughly half the settlement as well. And so often, if you have a profile of interbedded clays and sands, it's important to identify these transition layers and remove them. That's one of the really nice features about the program, is it does give you that option to identify and remove them. And because it's done so quickly, you have the ability to compare with and without the transition layers. Program's got some nice little features that I use. You can copy profile. So if you've got a CPT profile, you can duplicate it, so you can add a copy of it. And so on one of them, you can run the analysis with the transition layers included, and the other one with them excluded, and then click the overlay button and compare what they look like. So there are some nice tricks that allow you to play with that. Oh, excuse me, I think I'm losing my voice, which probably is a good guideline that we've reached our limit. Okay, so you can see the liquefaction is always a complex problem, but hopefully we've covered some of the major features here that guide you on how I do the liquefaction analysis. And the bottom line is there's never a single answer. You have to use your judgment in terms of what you think it's really going to happen, because it is a complex problem. The software is being designed that it will run the basic analysis, but it allows you to look at different options. So often, if you run the very basic analysis with no extra features added, then typically the result will be somewhat conservative. But the program does allow you to go in and start to sort of fine-tune the analysis to begin to home in on what is likely to be the more probable result if you're designing for a future earthquake. Okay, so that concludes. Hopefully Kelly got the 10. Yeah, we got far in excess of 10, but she's got the first 10 anyway, and she'll be sending you emails, and she'll send you the license key. So that concludes our webinar. What I will conclude, and we've basically covered all the elements that are in the CPT guide, basic interpretation in fine grain and coarse grain materials, sort of design of shallow and deep foundations, liquefaction analysis. So we've covered most of the main topics. So what I would do is that if you have suggestions of what additional topics you would like me to cover in future webinars, then email that to Kelly so that we can get a sense of what we'll cover in the next 1 or 2 webinars. And what we do plan to do is hold future webinars that will actually cover some of the other in-situ tests other than just CPT, and so sort of build it up into a bit of a course on site investigation. So over time we'll add additional webinars on other topics of drilling, sampling, and other in-situ tests. So stay posted for future webinars. Thank you.